Hi, my name is Grant Medford. In this presentation, I will be analyzing barbell back squat using kinesiology and biomechanical principles. I will discuss the normal movement pattern, anatomical structures involved, functional anatomy concepts, and the kinetic and kinematic principles that contribute to efficient movement. I will also evaluate production and discuss ways to improve performance and reduce injury risk. The purpose of the barbell back squat is a compound lower body exercise commonly used in strength training, rehabilitation, and athletic performance. The primary purpose of the squat is to develop strength and force production in the lower body, particularly in the glutes, quads, and hamstrings. This movement is also considered a foundational movement pattern because it mimics everyday activities like sitting down and standing up. In sports, the squat helps athletes improve jumping ability, sprinting power, and overall lower body stability. The movement begins with the barbell placed across the upper traps muscles on the back. The lifter stands with feet approximately shoulder width apart, toes slightly pointed outward, and spine in neutral position. The core is braced to stabilize the trunk. During the movement, the client lowers their body by simultaneously performing hip flexion, knee flexion, and ankle dorsiflexion. The lifter continues descending until the thighs are approximately parallel to the ground or slightly below. For this position, the lifter pushes through the feet and extends the hips and knees to return to starting position. This pattern is often described as triple flexion during descent and triple extension during ascent. Phases of motion. The squat can be divided into three main phases. The first is the descent phase, which is primarily eccentric. The second phase is amortization, or the bottom phase, which is the transition point between lowering and rising. And the final phase, which is the ascent phase, which is the concentric action. Joints involved in this movement are the hip joint, the knee joint, the ankle joint. Most of the movement occurs in the sagittal plane, which divides the body into left and right halves. The axis of rotation for this movement is medial lateral axis. Primary muscles for this are the glute max, the quadriceps, and the hamstrings. The glute max does hip extension, the quadriceps do knee extension, and the hamstrings do hip extension. The gastrocsoleus complex is also used, and its action is plantar flexion. Different types of muscle contractions occur during the squat. During the descent phase, the glutes and quads perform eccentric contractions to control downward motion. The ascent phase, these same muscles perform concentric actions to extend hips and knees and raise the body. Several functional anatomy principles are involved in the squat. The stretch shortening cycle, the force length relationship, and the force velocity curve, and the active insufficiency. Required range of motion for the squat is going to be hip flexion at about 100 to 120 degrees, knee flexion at 120 to 140 degrees, ankle dorsiflexion at 15 to 20 degrees. Limited ankle dorsiflexion can mean that your trunk, or a compensation for that, is trunk lean. Limited hip mobility is going to be excessive lumbar flexion. Lever systems. The squat primarily uses third-class levers, which means that the effort is between the fulcrum and the resistance. When calculating torque, you're going to look at force times the moment arm length. So for this example, we did our total system is 1,000 newtons, and our moment arm at the knee is 0.4 meters. This gives us 400 newton meters. This is going to show us why deeper squats increase knee torque demand by increasing the moment arm length. For work and power calculations, work equals force times distance. If 1,000 newtons moved 0.6 meters, work would be 600 joules. And for power, it is work divided by time. If the ascent takes 1.2 seconds, power equals 600 divided by 1.2, which is 500 watts. Force vector and internal versus external forces. External forces are going to be gravity and ground reaction force, or GRF. Internal forces are going to be muscle tension, joint compression, ligament tension, and GRF must exceed system weight for ascent, meaning you have to overcome the weight to ascend. This is a free body diagram showing us how things are moving and which direction forces are moving. Newton's first law applied is going to be body resistance change in motion. Resist change in motion. The second law is going to be force equals mass times acceleration. So the greater load, the greater force needed. And the third law is going to be action reaction, or GRF. Friction between foot and ground prevents slipping. This is going to be friction. The primary plane for the movement is going to be sagittal, with the axis being medial lateral. For our movement pattern, we have triple flexion and triple extension. We have a secondary plane, which is going to be the frontal plane, and this is going to help us prevent knee valgus. Common insufficiencies and injuries are going to be knee valgus, excessive forward trunkling, lumbar flexion, otherwise known as the butt wink, and heel lift. And the injuries for these are going to be ACL strain, patellofemoral stress, and lumbar disc stress. For our first corrective exercise, we have goblet squat. This is going to improve upright posture, core activation, hip mobility, and for motor learning benefits, the front load of the goblet squat improves our proprioception. For our second corrective exercise, we have glute bridge / hip thrust. This is going to improve hip extension strength as well as posterior chain activation. For our transfer, this is going to enhance force production in the ascent phase. Application in motor learning. We can use external cues like push the floor away, progressive overload, tempo control, and video feedback. Then you can practice variability, which is going to improve long-term motor control. The barbell back squat demonstrates multi-joint coordination, complex torque relationships, functional anatomy principles, and force production and control. Understanding biomechanics is going to help us improve performance, safety, and movement efficiency.